Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I'm very happy to have Mike Shepard with us today. Hi, Mike.
Hi, how are you, Frank?
I am doing well on this November 1st, 2021, the day after Halloween, as a matter of fact. So, Mike, where are you located at?
I live in Bloomsburg, Pennsylvania. It's kind of in the middle of the state.
Is there snow on the ground yet?
There is not. We haven't even had our first frost yet. So It's kind of freaky October.
Wow. We have turned the corner here. I'm in Phoenix, Arizona. We'll get down into the 50 Fs in the morning, and we still warm up to a good low 80s, mid 80s in the daytime. So we're still pretty warm. So that is a pretty awesome background behind you. That's one of the Apollo shots.
No, this is a remake from one of the recent, I can't remember which satellite.
Orbiter. Yeah. Somebody's going to kill it. LROC.
Yeah, LROC. It's like a tribute photo, they redid it. But it's much higher resolution. It's really sharp, and the picture's beautiful. So I like this as a background.
Yeah. Well, I think the PI or so is at my home institution at Arizona State University. So
I believe you're right.
I should remember that. Yay, Mark. So,
Mark Robinson, right?
It's all rock. Very cool. So Mike, what do you like to do for research?
I actually have two areas of research. I've been doing radar astronomy of asteroids for 20 years or so. I started doing that in the late 90s. I went to JPL for a fellowship and worked with Steve Ostro, who we consider to be the founder of this field. And it's a very small community. And the other topic I worked on and did for many years was photometry, so Hapke modeling, that kind of stuff. I built a lab and I literally measured the bidirectional reflectance spectra of lots and lots of samples, including we were able to get 6 lunar samples.
Cool.
And we published all that in the PDS. So that's my other kind of weird research area.
That's weird. It's very cool. It's very cool. And that is going to bring us to this very lovely PSJ article, Asteroid 16 Psyche, Shapes, Features, and Global Map. And Mike, take us away.
Thank you. So like I said, I've been doing asteroid radar astronomy for 20 years or so. And about 15 years ago, I had the idea of using the radar to look at all of the M-class asteroids, the so-called metallic asteroids that we could from Arecibo, and see what they were like. They're kind of ambiguous spectrally in the visible and near infrared, so we thought radar might shed some light on it since it's less ambiguous to rock and metal. Back in 2017, we published a shape model of Psyche using the first delayed Doppler images of it. And that model was being used by the Psyche mission up until recently. I had a chance just in a year ago or so. Catherine DeClear at Caltech has been using the ALMA, the Atacama Large Array Submillimeter Array Telescope, and she got some imaging data of Psyche. This is the first time it's been imaged like that. And she said, hey, do you have a shape model I can use and lay this on top of and take a look and look for, some correlations? We did it, and it didn't work very well. And the reason is because the model I had published was a little thick. So we agreed to redo the model using her data, which was fantastic. And that was where this paper came from.
Cool.
So this introduction is, we're able to do quite a bit of interesting stuff. The shape model and size of Psyche has really begun to converge by a lot of different people. So this introduction is just to introduce the 3 primary models that have been proposed for what Psyche is. The first one is it's a remnant core that's left over from early collision in the ancient solar system. So that model suggests it's this big iron lump, maybe beaten up and maybe covered by some silicate since then, but essentially a core. Another model is that Psyche was shattered completely and then reassembled gravitationally. So you have this mix of silicate and iron, kind of like mesositeritic meteorites. And then a more recent model that's been proposed is ferrovolcanic. There's two models. One is that it's still an iron lump that cooled inward, and that there were breakouts here and there of molten iron. But the one that I think is probably the most reasonable, at least the one we've decided is the most reasonable, is the latest, the Johnson et al. Proposal. That Psyche is a differentiated object like most of the other large asteroids, and has a silicate mantle and an iron core, but for whatever reason, as it cooled, molten iron, which was probably more volatile rich, erupted onto the surface. So you would have these iron lava flows or volcanic structures. But anyway, we decided to use this new model along with some other radar data we had to kind of look at which of these were the most realistic, or the ones that fit the data the best anyway. So the paper begins obviously with the data sets and the shape models. So we slowly, because Psyche is now a spacecraft target, a lot of people have been interested in it. So we were able to take advantage of the shape radar data, what we call delayed Doppler imaging. So these are two-dimensional images of an asteroid, and to make a shape model. And then we were also able to use these images from the Atacama Large Submillimeter Array. And we had some adaptive optics images. So if you want to just pop down to figure 1 first.
There's the adaptive optics.
Yeah, these are all the table data. I think the figures are more.
Shape model. Let me just get some globals here. Okay, figure 1.
So figure 1 shows the actual model that we ended up with. The way I did this was I show you the data and then the model we settled on. So the data is in the left column. And then the shape model is in the third column with the arrows. And the middle column is a simulation of what that shape model would generate to a radar beam. So that's how we converge on these. We fool around with that shape model until the simulated radar view matches what we see.
Okay.
And so, like I said, the shape is converged, but what you see is the long purple axis there with the big arrow on it is the spin axis.
Yes.
And then the short red peg is what we are calling the 0 longitude line. So that would be where our major axis runs. And then the intermediate green peg would be at 90 degrees longitude. And so this is the sequence of all of the delay Doppler images we had we took these in 2015 and refit with the other data as well.
Okay, cool. So
you'd pop down to figure 2.
Okay. Can I ask a question? When you do this fitting, is this chi-square? Are you doing like a Bayesian? What do you?
Yeah, it's a chi-square. So we start with, let's say, ellipsoids, which are just generic shapes and aspect ratios, very smooth. And there's a lot of variables to play with: the pole direction, the spin rate, its size, its aspect ratio. So you may end up in a situation where you don't know a lot about an asteroid and you're kind of guessing at everything. In Psyche's case, we had a pretty good idea of the pole direction from several decades of work by different people. We knew the rotation period very well from a lot of light curve data. So what it came down to for this model was getting the size and the aspect ratio and the shape. So once we had ellipsoids that fit reasonably well with the size and the aspect ratios, the A, B, C aspect ratios, we started, deforming the shape with spherical harmonic representations of the ellipse. So these are kind of large scale deformations that give you, is it more pointy at one end, or does it have a few, depressions here? And then once we found shapes like that seemed to hold together and were consistent, then we would turn those models into vertex models with, the mesh model, and then individual vertices could be tweaked. And now you start to see more fine detail.
Okay, cool.
One of the problems with this, or one of the arts of this fitting process, is that if you aren't careful, noise starts to be fit and you get these bizarre looking shapes and features. So you have to hold it back in a sense. And we call it putting penalty functions on things. And then at some point we decide, yeah, this is a reasonable looking shape. There may be a couple of 2 or 3 models that all have roughly the same chi-square. And we have to make a qualitative decision about which we think is more realistic, and look at individual features maybe to see that, this thing is fit better here in this model. So at the end, we have a model that's probably the best consensus for what all of these inversions are telling us.
Okay, thank you.
Yep.
And we'll slide down to figure 2. It looks like we
Yep.
have
Well, let's stop there. Okay, so figure 2 is actually new data that we didn't have in 2015. So Psyche was one of the first targets we looked at with radar back in, I think, 2005. At the time, we didn't have the power at Arecibo. I think one of the Clystrons was dead. Those imaging data that you saw in the previous image. So this is what's called continuous wave. This is where we just send a uniform, pulse to the asteroid, and then we listen and measure the change in the frequency, the Doppler shift.
Okay.
Now the Doppler shift, because of its motion in orbit, is compensated for because we know its orbit very precisely. But as it rotates, some parts of the ellipse are rotating toward us and some are rotating away from us. And so it gives us a Doppler spread.
Yeah.
That's what you're seeing here is the Doppler spread. And you can use these to kind of get an idea of, its width at any given instant. This also puts some constraints on the pole direction and the rotation rate, but here we're primarily using these to measure the overall radar albedo. How much of the radar energy does it reflect back to us? And so that number is like an optical albedo. It goes from 0 to 1, and 0 would mean it doesn't reflect anything, and 1 means that it reflects as if it's a perfect sphere made of metal.
Right.
In the case of Psyche, it's reflecting about 35% of the radar back to us, which is what we get from these images, or these graphs anyway. And for context, most silicate asteroids, the C and the S class, only reflect about 15 to 17% of the radar energy.
Okay.
So it's reflecting more than roughly twice on average what a typical asteroid would reflect, which tells us that it's got some significant metal content. These were taken in 2017. What's unique about them is that in the previous observations we had of Psyche in 2005 and 2015, the asteroid was giving us the same look. Psyche's got this resonance with Earth, so when it was in the window at Arecibo, we were always seeing the south mid-latitudes. We were not seeing the northern part of Psyche. In 2017, it was further away from Earth, but it was showing its northern hemisphere to Earth. So we got these images, or not images, but these data, which told us something about how radar reflective it was in the northern hemisphere. So that's what we're showing here.
What's the dash lines?
So when we send radar energy, we send a polarized pulse. It's actually rotating, so we call it circular polarization.
Yep.
And then when it reflects back, if it's mirror-like or first surface reflections, it will reverse the orientation. So we call that the opposite sense or expected sense of rotation. That's the solid line.
Got it.
And if it penetrates the surface, or if there's a lot of double bounces, we get what's called the unexpected sense of rotation, which are the dashed lines. Usually the dashed lines, the unexpected sense, are much lower than the expected sense of rotation. There are a few asteroids where they're comparable. The E-class asteroids, for example, are bizarre in that way. Ice would give you comparable or even higher unexpected senses of rotation. So Psyche is telling us, at least from these data, that most of the reflections are coming from the surface or near surface.
Right. Okay. Thank you.
Okay, so figure 3, I guess, is where I wanted to go. I was talking about the Atacama data.
Yes, there we go.
Yeah, so these were taken by Catherine DeClear, Caltech. And like I said, they're the first imaging data taken by ALMA of Psyche. They've done a few other large main belt asteroids, but they were particularly interested in Psyche, as you might imagine. And so on the left is, again, the data themselves, the images, and those have been smoothed somewhat. There's a lot of calibration goes into that to get something that looks reasonable.
Yep.
And then immediate right is the shape model with the same orientation, so you can compare the model with their data. Okay. And the beam size is over on the right, that little dot, that's kind of giving you the resolution cell.
Yeah.
And gives you a sense for how much of the detail you can believe in the actual images. The X, what we're pointing to there with the X, I'll refer to in a minute, that's a feature that was seen in the Atacama data that we didn't see in any other data set. Okay. It seems to be missing in my shape model, which is why you see next to that the question mark.
Right, without that, yep.
Right, so these data are actually thermal. They're measuring the radiated energy coming from Psyche. It's not a reflection of anything. So it's kind of like a thermal infrared or a heat map in a way. And things that are very dark to your eye optically might not be visible in an optical image, but would be visible in a thermal image like these. It's just one of our questions is this a region that's really there? Is this a feature that's really there, but it's just dark and we can't see it optically, and the radar missed it as well because of the aspect of the radar at the time. But that's what the X is referring to, an unknown kind of feature.
Same for ENF?
Actually, ENF are features that we see. I'll mention those in a minute, but what I decided, there were so many features that people have actually talked about that instead of giving them names, which will wait for the mission to arrive and some kind of convention to be settled on for what we're going to call these things, we just use the ICAO alphabet, the Alpha, Bravo, Charlie, Delta kind of things that are used in radio lingo. So Echo is the E. Actually, in this case, I deviated. Instead of calling it Echo, I decided to call it Eros because the asteroid, near-Earth asteroid Eros, has a feature on it called Psyche because of the mythology between Psyche and Eros. So I thought it was appropriate. F is Foxtrot, another feature that we see in our shape model. So I was just pointing out how they are visible both in the shape model and at least hinted at in some of the imaging.
Very cool. Very cool.
So if you scroll down to the next figure, I guess that's 4. Another data set that we used, these were, I'll come back, there we go. So on the left, these are very large telescope images. These were not taken by me. These were taken by, the names escape me there, papers by Ferre et al., Vikankowski et al., and Bernaza et al. I think Bernaza was the PI on them. Anyway, they made them publicly available. It was very kind of them. And they had maybe 15 or 20 of those. So they published a paper with a shape model as well, just 2020, I believe, just prior to ours, and used a whole lot of these images. We took a subset. So the ones on the left are the actual images. They've been heavily filtered, and they have to do, some convolution or deconvolution in adaptive optics, which gives them sort of an unreal look in a way, but the shapes are the most important part to us. And then on the immediate right is our shape model for comparison. And again, the letters refer to the features that we or others have claimed to see. So F, there's that foxtrot, and then you can see it seen in the side images there. So the two columns on the left are from a north polar view, and the two columns on the right are from an equatorial view. And so you get different aspect shots of Psyche at these different rotations. So the numbers right above them refer to the the longitude of Psyche according to our shape model that's facing the Earth at the time these images were taken.
Okay. Nice.
Okay, next figure 5, if you would please. Okay, so figure 5, back in when we did the 2015 observations of Psyche at Arecibo, they were able to observe it at Keck as well in AO. So the two columns on the left are from those data. They were taken in the KP filter. And again, the images are on the left and the shape model is on the right, so you can compare. In 2020, we did not get anything at Arecibo because, as you know, unfortunately, Arecibo
fell down.
is now tragically dead. But we were able to get it at Keck. We did not use the new Keck data in the shape inversion. We really didn't need to. If you look at the shape model and the images, they're pretty much spot on with what the model prediction suggests. And they're in 3 different filters, so the HJ and KP filter. So
nice.
Now then the next figure immediately below that, the one on the left was a fantastic new piece of information that was added. And there's a whole subculture of, observing occultations. A lot of amateur astronomers are involved in, and some incredibly dedicated to this. And so Psyche had been observed by occultation in a number of previous encounters, 5, I think, I want to say. And we used 3 of those occultations in our previous shape model paper. This one, I only used this one on the left here. In 2019, they had an incredible coverage of it. And then our shape model is shown against the chords that were measured by the various astronomers.
Okay.
And so it very tightly constrains the C-axis, the spin axis, which was the most uncertain in our previous shape model. And I think it really tightens up that axis very nicely.
Very nice.
We were able to actually use this occultation in our inversion high coverage. The one on the right is a previous 2010. You can see at the bottom there's what looks like a timing offset between the occultation chord and the shape model. Most intriguing to me is up at the top here, that dashed circle. So that's the feature I was pointing out earlier, where it seems to show up in Atacama. It seems to not show up in the imaging data, but an occultation doesn't care if it's dark or bright. If there's something there, it will block the stars. And interestingly enough, there seems to be a missing piece there. So again, we don't know if it's a real feature that we're just missing in the visible, but does show up in the ALMA, more thermal data. But anyway, that's why we're pointing it out there.
Cool.
Evolution. Right.
Squatter, longer.
Right. The other thing that these do is they help us really tie down the pole direction.
Yes.
If we shift it even slightly, they don't fit the occultation chords as well. All right, so those are the data that we used for generating that shape. And I think the next figure may actually show that. Yep. So on the top is our shape model from 2017. And this was the first full shape model published for Psyche. And it wasn't too bad, actually. But as more and more data have come available, especially the newer adaptive optics images, so that middle shape model there is is the most recently published from the Asteroid et al. Fantastic model. You can see it's thinner along the c-axis.
Yes.
But many of the gross shape features are very similar. And then, as I said, we used some of that data for our most recent model. We were able to incorporate the radar and the occultation, which I think they used in the Friedel model, as well as the ALMA data. And so, from a gross, pictorial look at these, they're very, very similar. They're indistinguishable, at least in their gross characteristics. Poles are within a couple of degrees of each other. The sizes are within a few kilometers of each other. The spin rates are identical. What radar can give you, though, that adaptive optics has tough time with is indentations.
Okay.
Face on anyway. So we do see a crater. We saw it in our previous model, and it's right there at the southern latitudes. It doesn't show up in the Ferreira model, but I guess I wouldn't expect it to. However, you do see they have a lot of indentations that they in their model. So again, I think a lot of this is going to be, it's hard to tell how many indentations are believable and how many are noise. And so there's always this kind of, this best guess. How much of this signal do we believe and how much do we not? So certainly there's something right there
right
on that side, which is a feature called alpha. We'll talk about in a minute.
Okay.
Let's see what figure 8 shows, I believe.
Okay. Yes.
Yeah, this was one of the oddities that I just was looking at this one day and I said, this is weird. So the traditional way of looking at asteroids is as ellipsoids, which makes a lot of sense. That's a natural kind of relaxation figure for a rapidly spinning object.
Yep.
And if you throw the ellipsoid over, this is, I think, from the south polar view, you see 3 places where it deviates from ellipsoid, and we called them Alpha, Bravo, and Charlie. They were called A, B, and C by, I think, Ferreira et al. And Alpha, they actually in their paper have it as a crater, which it kind of looks like one here as well. Bravo and Charlie, we saw Charlie, I think it was, in our previous model. They're just large flat areas.
Okay.
So it occurred to me, they're flat, so let's try something else. So I throw this rectangular shape over the top.
Yeah.
And they go away.
Okay.
The only place that deviates now from that is the alpha region, and then there's a little larger, it's missing mass here, which we called alpha west. I don't know if it's realistic or real or not, but when you have things that are rotating quickly, and if they're rubble piles, you do get some very geometric shaped, certainly in the smaller near-Earth asteroids, you get some very geometric looking things, non-spherical.
Yep.
But I don't know if that's possible for something the size of Psyche. But anyway, it was so unusual, I decided maybe it's worth pointing out anyway.
Definitely. Yeah.
And this table is a list of all the features that had been previously defined or seen or thought to be seen on Psyche. And again, we use those feature names, Alpha, Bravo, Charlie, etc. The latitude, longitude, a brief description about what they are, and where they were first referenced or talked about. And then based on their appearance in our model and previous models, how confident we were that they were really there. Again, a lot of times we're not sure if we're fitting noise or if we're fitting signal. So this alpha, the large, flat, or crater-like area, is certainly visible in all of them. Whether it's a depression or a flat area is, we'll know when we get there.
Right.
But it's certainly something there. B and C, these large, flat, missing mass regions, as we call them, they're almost certainly there. They show up almost in every shape model and data set that we have. Delta D1 was what we call a dynamical depression. We thought it was a topographical depression, but we did define it as a dynamical depression in our previous paper. By that, what we mean is it's a combination of the gravity due to the shape and the spin of the asteroid. So a place where the gravity would be higher and dust might accumulate or something. We thought we saw it in our previous shape model, but it's not in our new model. So we just say it's indeterminate at this point. We're not sure it's there or not. That was at the South Pole.
Mm-hmm. Yes.
This crater E, I called it Eros instead of Echo, is seen in our previous model. It's in this model. I think it's almost certainly there.
I like prediction.
And these are rough guides based on the resolution we have, which is probably in the order of 5 to 10 kilometers, believable pixel resolution.
Okay.
Foxtrot is a new crater or depression. We didn't see it in the previous radar data because we didn't see the northern part of the asteroid. There are hints of it in the both the Atacama and the BLA from the side, equatorial views, and it shows up in our shape model. So I think it's likely. I'm not positive it's there, but it's right at the North Pole. Now, Golf Hotel in India are not really features in the sense of depressions or anything like that. They're notable because they either have high radar albedos or they have high optical albedos.
Right.
And in a couple of places there are some potential topography there, but we don't talk about their confidence, at least for the shape model, because they're really not shape features. But they're noted in our paper and in several others in the past, and I'll talk about those more in a minute. Moroi and Panthea are two features that were first defined by Vikenkowski et al., later Ferret et al. These are craters they saw in their shape model, as well as regions of low or high optical albedo. Now, we did not see the crater they call Moroi in our paper, so it could be there, but we just call it indeterminate. The Panthea region, I'll show you in a minute, we did see a depression there. It's also a region of high optical albedo and high radar albedo. So I think it's pretty confident that it's there, something is there. And then the X-ray is the one that we pointed out before, where we're not sure if there's something there or not. If it is, it's probably dark. So it, of course, is indeterminate as well.
Okay, nice.
So the next figure is we have a 3D shape model, which if you download the paper, there's an MP4 associated with it. It'll rotate, and you can actually see the full shape as it rotates is viewed from the north, plus 20 degrees north and minus 20 degrees south. And you can get a sense for the shapes. We used a lighting model that emphasizes the topography. And then on this figure, not on the MP4, I just kind of pointed out some of the bigger features, the Eros, little crater, the Panthea region, which really don't see from that view, but from the other view, you can see it's kind of a depression from that angle, the way the lighting is. Alpha is, of course, quite visible, that big flat or maybe concave region there. And then there's other little dimples under the west on that right there, which may or may not be real, I don't know, possibly. And then the delta, which was one of the craters we thought we saw in the previous paper, it's certainly a place where dust and stuff would accumulate, but we're not sure there's any depression there in this model anyway.
Okay.
And then I guess figure 10 is the culmination of everything.
Okay.
Now the color coding here has to explain. So the Vikenkowski et al. And then later Ferret et al., they took and made their shape model in the following way. They took a lot of light curves. There are dozens and dozens of light curves. And then they had these beautiful adaptive optics images, and they had access to the occultations. And so their shape model was an inversion that gave them both the three-dimensional shape, and it also gave them the optical variations across the surface. So they inverted for two things at the same time, and were able to create this beautiful optical albedo map. Now, it's been known for 30 years or so that something was bizarre about Psyche's optical albedo. It has a very unusual light curve. So one side of it, the left side over here, as you would look at, is brighter in general than the right side. This is a, this shows you the whole surface, I guess. So we would call that the western part and the eastern part, if you will. So we took, because their shape model and our shape model were virtually the same in terms of aspect and orientation, we laid their albedo map on top of our model.
Okay.
The optical albedo there is kind of a guesstimate for the range that you might see variations from the mean, and that is a figure they have to estimate again. They can make a model where there's 50% variation in albedo allowed, or one with only 10% variation in albedo allowed. So they had to make a judgment, and they decided 20% was a reasonable variation. So that's what you're seeing here.
Okay.
And then we've labeled the areas that were seen in our model and other people's models. So the dashed line at the top in the northern area is Panthea. Eros is in the bottom latitudes. Alpha, Bravo, and Charlie are labeled. Those are the Bravo and Charlie are the two flat areas. Alpha is the area where there's a crater, possibly a large crater. And then West Alpha is that dimpled region just to the west of it. That and then on top of that are these diffuse white spots kind of along the equatorial region. Yeah, those are places where subsequent observations by the same group with the very large telescope saw optically bright places that were not in their optical albedo model. Okay. So these were visually seen in their VLT data. They didn't put them on their model, but they did point out the locations. So for our purposes, we just put these stylized spots on the map where they said they saw these brighter regions. And if you look at their data, you can see where they're talking about. We don't know how big these regions are physically, how bright they are compared to other spots, but we thought they should be at least pointed out on this map. The circles are radar albedo measurements that we've taken over a 20-year period. Yes. So we got a lot of observations in 2005, I think about 16 of them. We had about half that many in 2015 when we were doing all the delayed Doppler imaging. And then 2017, that's when we were able to observe the northern hemisphere. So those are the dots seen all along the top. Yes. Now we decided to break the optical albedo up into three general groups. Less than 30 are the smaller dots, or less than 0.3. So remember, just to go back to what we said before, the radar albedo is kind of an estimate of how much radar energy is being reflected. A traditional or a typical main belt asteroid, or even near Earth for that matter, will only reflect roughly 15 to 20% of the radar energy back to Earth. So you would say its radar albedo is about 0.15 to 0.2. 0.3 is considerably higher than most main belts, but it's very common among the M class. So anything less than 0.3 we put with the small circle, and then elevated regions are 0.3 to 0.4. Yes. And then the ones that are just really pop out at you, greater than 0.4 are the big circles. Yep, Panthea, Golf. Right, Golf, Hotel, and Panthea. Yeah. Now, so what we started to do is look for correlations. Are there correlations between the radar albedo and any shapes we see, or between the radar albedo and the optical variations that people have reported? And what looks like we see are correlations between the optical albedo and the radar albedo. So Panthea, that depression in the northern hemisphere, has one really big radar albedo. And then, as you can see, it's also optically quite bright up there. In fact, that was pointed out by Pikinkowski et al. When they first noted it.
2000.
Right. That was their paper was 2018, I want to say.
2018.
Gulf is the region in the southern hemisphere, and every time we hit the asteroid at that aspect, we got a big echo. And you can see it's just south of the flat area called Bravo, but it's also very optically bright. One other caveat I need to point out about radar and optical albedo. So the radar albedos are, you can, you have some resolution to it. It's, you can put these nice variations on this map. Radar albedo is a whole disk measurement. So when we hit the asteroid with a radar beam, the echo we're getting back is from the entire visible side. However, with that said, most of the echo is going to come from the subradar center, the point where it's normal to Earth, and a region maybe 30 or 40 degrees of latitude, latitude's the wrong word, 30 degrees radius around that point. When you get further away than that, the surface is more or less pointing away from the Earth, and so most of that energy should be reflected off into space and not come back to Earth. So most of these echoes, we would guess, are coming from regions within 30 or 40 degrees of where that subradar point is. So we can't distinguish any better than that. So it looks like Bravo is within that sphere of influence. And then Hotel, there's a big bright one there and a couple of intermediates. And although the albedo map shows that area of Psyche to be dark or darker than normal, you do have those two bright spots that were pointed out. And I don't know any more about those regions other than they said they saw bright spots in the data. So, it looks like, again, there's some kind of correlation possibly there. And then the most bizarre is over in the India region. So none of them are particularly bright.
Bang, 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 bang.
But they are elevated and it's consistent, but more interestingly, is that every one of those echoes that came back was what we call bifurcated, meaning that we saw two peaks, not at the center of the frequency where we'd expect, but offset to either side. So what that suggests to us is that there's two or more regions of radar bright separated by something that's less radar bright. And so every time we hit this India region that we got these kinds of bifurcated echoes. And you'll notice there's bright regions in the India region right below alpha and to the west of it. So that crater Eros just south of it. All of these would be in the so-called radar field of view where they might contribute to these echoes. So something's very odd there. Yeah.
Well, it's an interesting region anyway.
Yeah, it is. So, obviously our data is very coarse in resolution, and optical albedo map is, probably not perfect. But given what we see, it looks like the radar albedo regions and the optical albedo regions are correlated. High radar albedo correlate with higher optical albedo. Yeah, and that's cool. The conclusion from that. So then when we take these and we look at the models for what Psyche is and what it's going to look like when we get there, could it be a metallic object? Well, there's a couple things voting against that, I guess. First of all, all of the mass data for Psyche and the size data, which is now converged very nicely, tell us that overall its bulk density is around 4,000 kilograms per cubic meter.
Okay.
Nickel would be, if it's pure iron nickel, would be in the 7,000 to 8,000 range.
Right.
So this tells us that either it's a mix of silicates and iron, or it's a heavily rubble piled iron body, which with something that's 220 kilometers or so in diameter,
right,
it's not clear that that can hold together. So it's unlikely, I think anyway, that it's an iron object. despite, you know, the earlier pictures of what these objects look like. The second model, you know, is it a mesositeritic, a kind of iron silicate mix, is another model that, you know, is favored. There's observations of silicates on the surface with visible near-infrared spectra. There's even now been detected hydrated silicates on the surface, which are completely at odds with anything that's been, you know, violently created, like, you know, a core might be. Are some ways to explain those. There was a recent paper, I forget his name. He did actual experiments with by shooting meteorites at iron targets and then measuring the spectra, and they found that this glass was formed on the surface of these metallic objects, and the glass retained silicate signatures as well as hydration features. So it's possible that those kinds of things are there.
Kind of wild.
The model we decided we thought was the best fit was that Psyche is a silicate body, differentiated silicate body, but that it has these regions where you have very high radar albedo because there's a lot of iron. And the model that explains that best is this ferrovolcanic model, where you have local regions of iron volcanism in the distant past that still remain. Now, why are they brighter optically? Well, you know, some kind of process is happening at these spots, which can affect the optical albedo. You know, exact mechanism, I don't know. It could be, you know, maybe the stuff that's coming up with the iron is brighter. Maybe there's, you know, there's a lot of options for that. So that's the model we decided best fit our data.
Cool.
So I want to show you, if I can share my screen very quickly.
Yeah, let's do that. And before we get to that, let's slide up. And Mike, I want to thank you so much for walking us through your very lovely PSJ article here. Thank you.
Thank you.
And you've got the screen.
All right, so what I want to do first of all is just, this was one of the few optical or radar images we got of another M-class asteroid. This is 779 Nina, which is also, it's up in that range of very high radar albedo targets. But what you see is these two regions, and this is the unstretched and the stretched view, where there are these spots. So, and then there's something that's not radar bright in between, which is very similar to the kind of thing we're seeing on Psyche. And then the other image I wanted to share is this. This is from a paper we did in 2015, published. As I said, we've been looking at the M's for 15 to 20 years, and we, at Arecibo, we were able to bounce radar off of a large number of them, 30 of them. And their radar albedos are shown here on the left, their asteroid number on the right, so x-axis, and then on the right is an estimate of surface bulk density based on the radar albedo. It's a very crude estimate, but it's something. And so we see these regions where the typical S and C class asteroid is in this hatched green area. So this is where most asteroids would fall. You can see there are some of them, you know, I think that's Clotho, and 77, I can't remember what that is, Freya, maybe 83 is Beatrix. So these have typical main belt asteroid radar albedos, and so they're probably not a lot different from the others that we see. The really high albedo ones are up here.
Yes.
Now, some of these have been changed, so we've revised. This is Cleopatra. We've revised that number. Cleopatra is now down here. Did a paper in 2018 with a new shape model for Cleopatra. Okay. 758 is a real bizarre one too. Nice. And then Psyche, this number has been, you know, revised. Now we're down in here. But here's our uncertainties. But you can see maybe a third of the M-class asteroids fall in this range. And then there's a whole group that fall in here that are kind of in no man's land. where they're higher than your traditional asteroid. They're not this high. And the one that, that I like to compare this to, let me see if I have it up here, is here.
Yeah, there we go.
So this is Lutetia,
Yep.
an M class, and Rosetta flew by.
Hmm.
And, for a while, we're thinking, is this another metallic one? But it's not. You can see it's very silicate looking. The spectral analysis suggests that it's maybe some kind of high iron silicate, like in carbonite, or there's a number of meteoritic analogs that might fit this, instantite chondrites. But anyway, so the conclusion I would say, that, at least in my mind, is that when we get to Psyche, we're going to see something that looks a lot more like Lutetia than we were expecting.
Okay.
But then there's going to be these really cool regions where we've got a lot of iron for whatever reason, and volcanism is maybe the most likely. But that's my revised view of what I think we're going to see when we get there.
Probably won't be the first revision.
No,
it's the way things work. And just to remind people, when do we expect to start getting early data back from Psyche?
Well, the mission launches next August, I think, and then it's supposed to go into orbit right around Groundhog Day in 2026.
Yes. Okay.
So, the first orbit, they got a series of 4 orbits. They're doing a very Dawn-like kind of mission profile where they stay away and orbit from a very safe distance until they get the gravity profile figured out.
Right.
But right away, we'll be able to see if my shape model is garbage or not. So I'm both terrified and elated at the prospect of that.
The excitement of predictions, I tell you, it cuts both ways.
And after, I think, a couple of months, they'll have the gravity model figured out a little better, and they'll descend to progressively closer and closer orbits until the final set of orbits, which is near the end of mission life, is designed for their X-ray, gamma ray spectrometers, so they can get elemental abundances and really map it at a little higher resolution for elemental kinds of stuff.
Very nice. Awesome. Well, I cross my fingers on your predictions on the shape models, and we will see what happens when we get there. Be very cool. Mike, I want to thank you so much for, again, sharing your very lovely paper and thoughts on Psyche 16.
Thank you very much for having me. I appreciate it.
All right. And that'll do, everyone. And I hope this made your astronomy day just a little bit better, and we will see you on the next one. Bye-bye.